We are today implementing right now. So this is twitch.tv services. Is it? There we go. Cool. So what are we doing? Now that I fixed all that stuff, it's time to implement. So I fixed the way. So I fixed the whole factoring and all that stuff, and it now seems to work well. And I know I should be working on making sure this is a bit more robust too, and I can actually build test cases. Um, but I'm thinking that's really a prototype, and it's not functionally finished in terms of that I'm happy enough for this to be a prototype. Now I'm not fully so now I can step through factorization of qubits, which I like, right? So here I have an example um, of the simple system that is a um, let's just quickly recap what we've done until now. So I was working on this specific case just to show how can one see, or to show that at least phase kickback works, because that was something that was unclear. So for this particular case, we have a phase kickback here, right? And so this is the circuit, and then if you factor the qubits, but you just take a look at step 0, this means essentially don't factor them, right? The system is in a sort of in its most expanded way. So you have four potential, four potential hyperedges, and actually they're all kind of mapped to this is 0 0, this is 1 0 1 0 1, this is 1 0, and this is 1 1. But you can actually factor this out, right? Um, I mean that's really this. It's a this is if you don't factor it, that's what you get. They actually get the wave function, right? So this is not factoring the qubits gives you just a wave function, but you can factor the qubits out because some of these things can just be this can be actually factored out into and I don't know if factoring is the right is the right naming for it, but the idea is you can express that as the two qubit states separately in this case because there's no entanglement. So what factor qubits is going to try to do is it's going to try to separate these two qubits, right? And it's going to stop when it cannot anymore, and that will show you either that the system is not entangled or it will show you how the entanglement looks like, right? In terms of which states are correlated in between the qubits. And so, yeah, what this is doing is basically taking. I think one thing that we have to do, but this is for later, is so verbose. So basically to do out of verbose mode, that explains a bit more what's going on. So I just because I think out of the so what's being merged and stuff like that. Because remember, the goal of these is just really to be a bit of an sort of a self-exploration tool, the same way that Quirk really is, right, where you can just play with things and in a really smooth way, and eventually maybe just the core of these, the sort of the hypergraph representation and the factorization algorithm, which is just maybe there's more efficient ways to implement that than the way that I'm doing it. But the idea is, I'm even thinking to just have it as a display in here, or yeah, kind of, you drop like a hypergraph sort of display and basically see sort of the hypergraph um, and see how this factors out. I don't know. We'll see. I'm still there's plenty of things to do. I also don't like the fact that for some common and well-known states like the 0, the 1, the plus, the minus, like computational basis states, like I think I should also have a cleaner representation that it's easier and it's an easier catch to the eye. Anyway, so this is doing its thing, and Mm, so this is doing its thing. Do, 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 do. And eventually, uh, you're factoring things out because in between the edges you have nodes which have the same state. For example, between these two edges, Q0 is in both cases, Q0 is in the zero state. And so you can factor this out, and then Q1 just becomes a plus state. Um, yeah. Or a minus, as a matter of fact, because there is a minus, there's a sort of a complex number here that it's a sort of a multiplicative factor, just to make sure that we keep these nodes as pure as possible, as clean as possible. And that multiplies, and so you're actually going to have like a minus state. Anyway, so you factor things out, and at the end you end up with a system that is in the minus state, right? So for both qubits, which is correct. So that works because it didn't work. Now I'm going to get rid of all these. Gonna get rid of all these. Yes, gonna get rid of all these. Okay, cool. And now it's time to implement measurement. And I'm thinking, so the reason I want to implement measurement is because I want to allow the user to basically explore, the effects of partial measurement on an entangled state, right? Which is basically at the core of Shor's algorithm. It's at the core of Simon's algorithm. It's at the core of some. It's a well-known technique, right? Now I'm struggling with sort of the notion of measurement because I think the problem is that the notion of measurement comes attached with a lot of the sort of the experiment related stuff, like how many shots you're doing, define the experiment, measuring on a certain, on a given basis and stuff like that. And I like the fact that Quirk kind of doesn't do these. It really embraces the fact that it's like, I'm a simulator. I can show you the state. Um, like these, I've always struggled with this gate because to be honest, assuming measurement deferred, like, okay, I guess this is, I guess this gate allows you to do some post measurement stuff, right? And say, I'm going to measure these, and if it measures 1, then I'm going to do that. If it measures 0, yeah. So it turns these, like this is, I'm not so sure how helpful this is in terms of, so where is he's using these in, I think, teleportation. Yeah, because teleportation is basically you measure stuff and then you do things, right? When you're measuring, because the thing is, I guess how is that implemented? Because I was thinking the pulse selection is another interesting mechanism. Um, Give me a second. Okay. So I was thinking that pulse selection is an interesting mechanism to implement as well. and I'm not sure which one to go for first, because measurement would allow me to but how that works? So here what you're saying is, what this is doing is saying, okay, now we measure, and then I think, well, after this measurement, let's see, after the measurement is done, measure deferred. I think after the measurement is, this is just so we know, okay, I don't know. Because if I, instead of a measurement, yeah, like that stays the same. I think that doesn't do anything, because Quirk's philosophy here, yeah, okay, it does change the state of the specific qubit that you're measuring, meaning it tells you the outcome of the measurement, which is like, yeah, so which is like, if I have if I do these, right? No, not these. So let's just do these. Yeah. So what this is doing is telling me, well, I don't know. Like here I know the state, but if I measure, right? Like, yeah, okay, it turns that into that's really a classical. Yeah, the density matrix will show you these. Yeah, that's what it does. So it literally turns these into just a classical state of, yeah, we can measure 0, 1, right? Um, but I'm curious how would, because I also feel that the hypergraphs thing could be used to represent mixed states as well, because we have the concepts, I have the concept of different nodes, representing possible states of the same um, of the same system or the same qubit. And to be honest, when we look at a simple example, like doing a, let's just do, so we do a Harman gate, then we do a control NOT gate, system draw, right? That's essentially what you have is, well, if you take a look at Q0, we know that you're going to measure a mixture of 0 and 1 because they're on different edges. So if I were to say, okay, maybe that's the easiest first step, and maybe that's a way to say, okay, given a system, like I want to measure 1 qubit, so I want to get these. Mm. But still, that does not change the overall system, does it? Like, would I expect that if I just like, take a look at the just the function gives, gets a qubit or a set of qubits, maybe first with 1 qubit, and as like measure this qubit, and I get a probability. Like, why would that be useful? Well, it tells me what is the probability of measuring certain state. And then with pos selection actually would transform the system hypergraph, right? Or because if I do measurement, it basically what would this be? So how would the equivalent be in my system, right? Because what I want to do, I mean, I like the fact that a measurement in Quirk does not, like, you don't have to tell Quirk how many shots you want to do and all that stuff, right? So you're telling I want to measure, and so you're turning your quantum state into a classical one. And now you have a basically sort of a mixed state. Yeah, you basically have a mixed state. Like if I use another gate, say, I don't know, like this, right? Like, yeah, that just exactly, yeah. How would I represent that in my system in a way that that it still makes sense? Like how do I account for these classical? This is complicated, right? Like, but I think that's the specification that I want to have is the same like you have in Quirk. So measuring is just it's just projecting. It's just a projection. So just project it. Just project the state, and that's it, right? That's what I want to do, and I just want to leave the hypergraph as is with that item sort of. Hmm. I can still, like, can I still do things like this here? I can, yeah, I can still perform. Whoa, 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 what's going on? What happened? Quirk. Computing circuit values failed. Boom. Okay. I'll probably report that later. No remix. Sorry. So this is not allowed. This is not allowed. This is allowed though. But it's not, so it's not allowed. Okay, so we're only allowed to do things that change along the z-axis. Are we? No remix, yeah, because that would. Okay, so somehow I have to figure out a way to get these implemented, because so this is one thing, and then the projection is another thing, right? So and then the sort of pos selection. Pos select. So there's not going to be shots. So there's definitely not going to be shots. And here for pos select, we need to know I want to know, do I need to put an operation, I guess? Pos select a state? I think so, right? So would be to say, I have this qubit and I want to pos select for on states, right? So that basically, leaves me with these. So what pos selection does is it's in the way it's implemented in Quirk, it does not, like it, you can still work with the qubit, right? So you can still do everything else that you wanted to do and stuff like that. So this is pos selection and this measurement. To be honest, I don't know which one is the nicest to work with, but we can start with measurement, try to figure this out. So with the density matrix is obvious what's happening. But how would I represent these here, right? So what I essentially have at each node is it's just a state vector. And I cannot represent a mixed state. Can I represent a mixed state with a state vector? Let's see. State, max information state. I'm not sure what it means, but I guess it means if I apply a number of prayers. Cannot do it with mixed state. Apparently, I can't let act an operator on a mixed state. It already starts with the fact that a mixed state is mathematically described by a matrix. So it's no longer a state vector. Why has it to be described by a matrix? So we don't really know which state systems. Yeah, but maybe, okay, so I just, the this kind of state in terms of a set of basis vectors of Hilbert space. The shortness is no, meaning that we can not write down a definite state vector x or x in the form where are known and unique. Whenever we can write down such state with all coefficients known, then we say our system is an pure state, which means the definite ket is statistical distribution, very much similar to the concept assembles in classical statistical mechanics, where adopting the same notation as before. X is a mixed state, which you can as an ensemble of various possible definite states. Okay, so I actually can actually, yeah, do it as a in an ensemble way, where then B and PB correspond to the fraction of the respective states in that ensemble. For mixed states, we have no choice but to discuss system in terms of density operators as opposed to kets. A mixture of states, which you can interpret as statistical distribution. Let's assume on a measure, we know the expectation value of O for each state, to extend this to a whole ensemble, knowing the fraction of times each state occurs in the ensemble average value O is the weighted average of all the expected values. No, whatever. So I'm thinking a way to do this is to just So what would be the best way to implement that? Is just to say that, for example, Q0, like what if I, so this is this basic example, right? So let's just take the basic example of First, let's just do one qubit, okay? So we're just doing one qubit. We're just doing one qubit, so it's all chill and cool, and we have just these here, right? And I think what should happen is that we should just basically have two nodes. I think we just should have two nodes. The question is, should we have two edges? Probably. Because essentially, that is really what we're doing. Like when I'm entangling, right? When I'm doing that, essentially, like I have a similar effect. Like yeah, that is actually behaving like if these would now be a mixture of that, because we don't really know with certainty. And the way that I currently represent this with the system, so to be the most consistent, that should be the same. So if I measure, what I should do is I should kind of basically split the cube, split the whole thing, right? Split the so I measure a qubit, and I basically split that into two edges, right? And each edge has an actual definite quantum state, right? So I think that's what should happen with the measure. So if I do system measure and I give it Q0, that's what should happen. Now, what happens if I have, what happens if I have two qubits and they are already entangled, right? So that's a matrix. That's what it is. And if I measure these, and nothing changes, to be honest. Yeah, that's because that's just, I think I think that is really it. Like if I have a system, let's just do another. It's cool because it almost feels like measurement and entanglement are just mathematically the same, at least at the model level. So apply a 2-qubit gate. How was I doing that? So Q0, Q1, so if I the gate, what am I missing? Oh, I'm stupid. Okay. Well, sorry. There you go. So if I just want to measure here, yeah, that is just basically like nothing changes. Literally nothing changes. What if I just want to measure one? Like, should that anyhow change? Like if I am, just say measure qubit 0, well, it's already measured. There's nothing to measure. How do I know that? How do I even implement this? I have an idea. But I hope that this is understandable, at least in terms of the way that I'm thinking about this. Like, what I'm saying is that measure should basically, what it should do is it should modify the system in a way such that um, I no, not project, but yeah, kind of like I take the node and project it into the computational basis states. And so that essentially means splitting the thing. Now, so for this case, a measurement would not do anything. But what about this case? So what about this case? I have 2 qubits. I apply Hadamard. Like, what about the, yeah, what about this case? And I probably want to factor the system. Probably want to factor the qubits. Factor qubits. And just give it like this stuff. So I have, let's say I have this system, right? And now I want to measure Q0. Let's see what Quirk says. So I have the system. Cool. So, and I want to measure Q0. That state stays as is, right? But this one gets sort of classical. So how would we represent this? What we represent this by would we represent this by saying that like, do I split that into 4? My intuition tells me I should split these into 2 edges, each of which will have one of the computational values of, yeah. I think that's what should happen. I think it's just a as a result, I should get. Let me see if I can draw these. I can open Paint maybe. The old beloved best in class painting tool, right? And now I'm going to use, if this works, so good. So I have a system that is in the plus state, and that's like just my system. And then this is Q0 and this is Q1, and I want to measure Q0. My guess is that this should split into 2 edges that look like these, and that both have the probability of like, well, no, that actually should be indeed just a damn it. It should be, because here we clearly have 50%. And I think that the problem is that the way that I've designed the edges, they hold a complex number. So maybe I should still use that. But I'm not so sure if this is correct, but we can just go with that for now. So that would basically, what that would do is, so you would kind of have the 0.7 blah 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 and the 0.7 blah 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 as a sort of coefficients for the hyperedges, and that would just really be your system. But if this is the case, I'm not so sure I can get the right. Yeah, Yeah, it's almost like the measurement is just a controlled identity. I don't know if you can do that. Um, or am I talking or am I talking shit? Maybe I'm talking shit. Can I do this in Quirk? Quirk meaning. I know what Quirk means, man. Quirk. Quinoa. Um, what I was trying to do is so this, and these, and now can I do a? No, I can't control for these. There's no identity, is there? No, but it can control measurement. No, yeah, can't control. Sorry. It almost feels like, ooh, fancy. You can control post selection. Yeah, I don't know. I think I can't really put this in Quirk, but it almost feels like these. The problem that I'm having is that I can't possibly get the proper wave function, although I don't know if that's something that you can do. Well, you should, and it should still be the same, right? If I measure, all I'm saying is these things are not anymore like quantum states. They're just a mixture of zeros and ones, right? Um, and so, yeah. But I'm not feeling comfortable with these because I don't know if this just shouldn't be, if this just shouldn't be 0, 0, and 0, 1. Yeah, but that would actually merge. If I do these, that would actually merge into the zero, into 0 plus, really. Yeah, and the problem. Okay. That is indeed, that it does indeed seem like it's a control identity. It's just pretty nuts. It's just the fact that I can't allow these to merge again. Like these things don't merge anymore. They are classical. So I should flag this somehow in the nodes. So this is for sure something we have to do. So let's get to right. So let's try this approach. I'm thinking, yeah, I'm thinking like it's almost like a controlled identity, mathematically speaking. So I'm kind of saying, um, if it's 0, don't apply any gate. If it's 1, then apply the identity gate, which basically you would conceptually split the system like these. But now, these have been they're not quantum anymore, so I can't merge them again. But I think that's definitely one thing that I have to add to the whole concept here is that a node can be a hypernode. So a node self quantum equals true. So a node is in a quantum state, right? A node is quantum by default, but what the measurement would do is it would turn these node into not quantum. And when the node is not quantum, then I probably have to make sure that I don't apply certain operations to it because I can't. I should probably not allow any operation to act on that qubit, and these qubits can't merge for sure. So this is going to be interesting. So this is going to actually span through. Yeah, this is going to be. I'm going to have to touch the entire code base or the entire prototype code. Yeah, basically making sure that if a node is quantum, I shouldn't touch it. well, at least these things can be merged. That's for sure. That's for sure. So let me add these. What is the factor recursive? So for sure, if a node is it's not quantum, can be merged. That's the idea. Because now it's classical, so we know it's either this or that, and we just can merge it. But I like the fact that I can reuse the same concept of the hyperedges to represent both entanglement as well as a measured system, because that's basically mathematically what happens is that you treat an entangled state as a mixture, right? And so yeah, so basically that's kind of what happens. So I think, how would a control identity look like? So this is a control Z. A control node. I think it's just basically. This is really a hack, right? I'm just hacking this because, so obviously the controlled identity is like applying the identity to both. But I know that if I use my internal implementation of apply 2-qubit gate, I know that I'm doing the splitting that I have to do first. So I'm actually kind of calculating the local the local state vector of these 2 qubits. Okay, the problem is that's bullshit. No, that's not how I should do it. I think I should do manual splitting here. I should do manual splitting because it's not going to work if I have more than 2 edges. Yeah, so I think I have to just do literally. And if I have, and I guess that if I have, I guess if I have 2 edges, or I have multiple edges, and in some edges the system. Okay, let's try to find another complicated example. So I initialize. I have 2 qubits. I don't have, sadly, a control Hadamard gate, right? I haven't really implemented that. I don't even know how that would look like. I think it would probably look like. Ooh. I kind of liked an earlier version of the 2-qubit gate that I had, which is apply control gate, because it was really generic in terms of what it was allowing me to do. Like I could just control Hadamard matrix. There's the matrix there somewhere. The hell, someone's calling. Okay. So that's the control Hadamard. Okay, yeah. Yeah, okay, you have the little Hadamard here at the bottom. So actually, let me go back. Why did this open another window? I don't know. So this is probably the controlled Hadamard, and then I have basically, this is here, this is here, this is here, and this is, well, here, right? That is, what have I done? Control Hadamard. This is here, this is here, this is here. and this is here with a minus. So if I apply control Hadamard to this example here, control Hadamard, Jesus, control Hadamard. So, oh, well, gotta run this first. That's not what I wanted. Yeah, okay, so this is a good example to work from. So what would a measurement look like here of qubit 1, right? So, yeah. Okay, let's say we're doing these. So we have the system, which is, yeah, basically this system, right? And now I apply a measurement here. That's not really, well, let's do it like this. Yeah, I mean, it's just, I guess it is just, yeah, it's just projected. It just projects this, so it just, the density matrix is just the probability of each. So I guess what these would do, is it would split, so it would not touch this edge. I'm trying to think about like sort of the algorithmical process of these, right? Because I have to account for the cases where we've got edges or we've got no edges. And I think that the same implementation scenario that I've built for the 2-qubit gate applies here. So I just go edge by edge, right? And check, like, do I have to project this gate or not? Like, and in this case, I don't have to touch this edge. But in this case, I will have to, so what I will have to do in this case is I will have to split this edge into two, which will have a 0 and a 1 node in here. But I can't merge. Like I have to flag all the nodes being quantum false and they can't be merged anymore. I think that's what I'm going to go for first, and probably not today because I don't. But let's try to scaffold that. But that would be the idea. So I think the idea would be the following. So first of all, we need to iterate over each hyperedge, right? Now, if the qubit, this qubit is in. If the qubit is in the computational basis, then we just flag it as quantum false. And if the qubit is not, then we need to split the edge into two, where each will have 82, so one where the node will be in the 0 state, and one where the node will be in the 1 state. Also with quantum false. Yeah. I think that's how I would implement measurement. I think so. It's been, so let's check. So any questions? If not, I think I'll probably leave it here because it's 15 minutes. I got like about 10 minutes left, so I think I'll just try to stream tomorrow again, actually trying to implement these. But I think that's the Roth approach, the Roth structure for implementing measurement in here. It really almost feels like it's surprisingly and like mathematically similar to entanglement, right? But because that's really what we're doing. So we're basically saying, oh, and actually that's gonna have, oh, that's gonna, I think that might break. I need to revise preconditions for the op methods because update the rest of the code base to account for non-quantum nodes. So this is a to-do and this is a to-do. Because essentially it's the same like Quirk does here, right? So once I've measured something, like I cannot, I shouldn't be able to apply something like these. Like I can apply, probably can allow for gates that flip the beat, you know? It's funny because this gate does actually change the phase. So why is this even allowed? Okay, but it's not in the sense that with measurement deferred. Okay, so this calculation is like if we defer the measurement. I think in my case, I think I just won't allow. Think won't allow for any gates. It will make things easier. Probably don't allow for any gates on non-quantum nodes. Maybe bit flips, but this may be later. I don't know. I'll see. Just it's too, yeah. And I think post selection, to be honest, is going to be the same or similar, but we'll actually cat part of the hypergraph and just drop it. Because if I post select for one, right? It's just I don't know how a post select for plus would look like, but if I post select for one, that's what it does, right? So it just actually keeps, yeah, it just omits part of the whole, but that's another story. So, but I think I'm happy with the way this is structured. So iterate over each hyper edge. Yeah, we'll see. I'll try to get streaming tomorrow or in a couple days, see if I can start building these. But I'll have to recheck whether this doesn't have any impact on some of the preconditions in the other functions where I was like, oh, maybe, I'm sure there's not going to be only, that there's going to be just max one node, but I think that still holds, just maximum one node per branch. It's just, in this case, we are not allowing for merging to happen. Kind of feels nice. I don't know. Anyway, I hope that was helpful. And I hope that, yeah, I mean, whatever, I guess. Cool. Happy with the progress, at least conceptually here. Then see you tomorrow or in a couple days. We'll see. Bye-bye.